the table. Now that we know what we know that that was the least efficient method, but conceptually it kind of shows you what is going on. So we're going to start similarly, but this is a totally new type of function. This is what I would call a jump function. It's kind of a mixture between a rational and an absolute value, which we did see a little bit of when we kind of examined this type of problem, right? That essentially, we talked about how that became the absolute value of x over x. But we really did that and looked at that as it referenced end behavior. We didn't do too much with that type of function anywhere else other than end behavior. So this is a jump function, and we're going to look at the parent graph of that right now. So if we plug in -3, the numerator will be 3 over a denominator of -3, which will be what? -1. If I plug in a -2, the numerator will be 2 over -2 in the denominator, which will also be -1. If I plug in a -1, the numerator is 1 over the denominator of -1 is also -1. 0 does not exist, right? If you plug in +1, you'll get 1 over 1, which is 1. You'll get 2 over 2, which is 1. You'll get 3 over 3, which is 1. It makes sense that all of these answers are 1, essentially, right? Because x divided by x is 1. It's just that with the absolute value on one of them, it always keeps the numerator positive. And then if x is a negative, it will be a positive over a negative, making it -1. Whereas if x is positive, it'll be a positive over a positive, keeping it a +1. So when you go to graph this, what you'll find is that at -3, we're at -1. At -2, we're at -1. At -1, we're at -1. At any negative number, we're going to be at -1. So not at 0, that'll be an open circle, but everywhere up until 0 will be a positive x over a negative x, which is -1. This whole section is positive x over negative x. Versus once we get on the other side of 0, it's going to be a positive x over a positive x. And you'll always be +1 on that side. And that's the parent graph. Okay? The jump function title is pretty self-explanatory. It jumps. Okay? Piecewise functions jump too sometimes between the pieces, but this is what's actually called a jump function. Okay? So your limit as you approach 0, and again, we know a lot more now than maybe the textbook thinks we would, but obviously if you approach 0 from the right, what's the limit? If you're approaching 0 from the right. Marissa. 1. As you approach 0 from the left, Mackenzie. -1. Those do not match, so the overall limit does not exist. What is our limit as we approach 2, Olivia? Good. Sarah, what is our limit as we approach -2? Good. Okay? If you jump down to the second exercise, sketching g of x, the whole transformation concept is the same. So if our parent graph was f of x, this is now just f of x minus 3, which means this graph is going to be shifted 3 units to the right. Yes? Shift 3 units to the right. So we could recomplete a table of values, Or you can kind of see that this is going to not exist at 3. Can we all see that? You are not going to have the graph exist at 3. But anywhere greater than 3, it's going to be a positive over a positive version of itself. And anywhere prior to 3, it's going to be a positive over a negative version of itself, which is going to still keep us at 1 and negative 1. So same jump function, just shifted 3 units to the right. So our limit as we approach 3 from the right, Nate, is what? 1. And our limit as we approach 3 from the left, Bailey? Good. And so our overall limit as we approach 3 does not exist. Okay? The next exercise is going to show us kind of where this jump function is hidden. On the forefront right now, it definitely does not look like a jump function. Agreed? Okay, but if you factor this, that denominator is going to factor into x minus 1 squared. And then the square root of something squared brings us to the absolute value of x minus 1. So it still doesn't look exactly like the jump function parent graph, because in the jump function paragraph or parent graph, the absolute value is on the numerator, right? Here it's on the denominator, but the concept will be the same. If you're at 1, it's going to not exist. 1 is where this graph doesn't exist. Anywhere over 1, you're going to get a positive over a positive version of itself, so it'll be 1. And then anywhere less than 1, you're going to get a negative number over a positive version of itself, which will put you at negative 1. But you have to factor and take the square root and know the absolute value feature there in order to accomplish that. So our limit as we approach 1 from the right is 1. The limit as we approach 1 from the left is negative 1. And the overall limit as we approach 1 does not exist. So wherever this jump is occurring, the limit does not exist. Unless it's a kind of a freaky incident and like somewhat unique. And if we get to that, if there is one of those, I'll show it to you. Good? Okay. 1 over x squared, this is nothing new. This is just me reinforcing some asymptote behavior, because we all know there's an asymptote at 0, yes? Nothing factors cancel, so there's no holes. And the denominator has, if x is 0, would be undefined. So there's where our vertical asymptote is. The thing I'm trying to reinforce here is that since it is an asymptote at 0 with a degree of 2, it's kind of got even-like behavior on either side of that asymptote, meaning they're images of each other. It's also still small over big. So in terms of a horizontal asymptote, that's the x-axis. But 1 over x squared just looks like this. Right? Whether you put in a positive 2 or a negative 2, it's still going to be 1/4. Whether you put in a positive 10 or a negative 10, it's still going to be 1/100th. So as you approach 0, you're approaching an asymptote. So the limit doesn't exist in general, but if we can get more specific, we will. And so from the right, it's going towards positive infinity. As we approach 0 coming in from the left, it's approaching positive infinity. Those two infinities actually are the same type, both positive. So this answer would be positive infinity, which is just a more specific version of does not exist. Good? Okay. All right. There are some rules for trig functions that we will talk about. But I set up this table of values for you. So can we all agree that this is not a traditional sine graph, right? I'm not taking the sine of x, I'm taking the sine of 1 over x, which makes it a little bit different. And so when I plug in these numbers, 2 over pi versus 2 over 3 pi versus 2 over 5 pi versus 2 over 7 pi, since the numerator is staying 2 and the denominator is growing, what are these numbers getting closer and closer to? If your numerator remains a constant and your denominator grows, it's getting smaller and smaller, right? Eventually towards 0. Eventually at some point we'd get to 2 over 99 pi. That's going to be a tiny number. So let's kind of plug these in and you'll see what these specific choices that I put on there make happen. So if I do the sine of 1 over x, I'm really taking the sine of the reciprocal of this. Agreed? So what is the sine of pi over 2? 1. What is the sine of 3 pi over 2? Negative 1. What is the sine of 5 pi over 2? Nope. All right, so for those of you, I'm sure we lost some people here. Sine of 0 is 0. And then in your sine graph, it increases up to 1. So there's pi over 2. Here's pi, aka 2 pi over 2. Here's 3 pi over 2. Here's 4 pi over 2. This would be 5 pi over 2, 6 pi over 2, 7 pi over 2, 8 pi over 2, 9 pi over 2, 10 pi over 2. You follow? Okay? So the sine of 0 is 0. The sine of pi over 2 is 1. Then the sine of pi is 0. And the sine of 3 pi over 2 is negative 1, and that cycle continues. So the sine of 3 pi over 2 being negative 1, moving to the sine of 5 pi over 2 puts us back up here. Yes? Back to positive 1. 6 pi over 2, 7 pi over 2 is down here. The sine of 7 pi over 2 would be back to negative 1. So here we have a function that is constantly oscillating back and forth between 1 and negative 1. Let me show you this on a graph. So the sine of 1 over x is my function. I'm going to be in radians. My window, I'm going to start at 0 and I'm going to end at, I don't know, 2 over 49 pi. Maybe I won't go. Maybe I'll just do 2 over 19 pi. I'll go bigger if I need to. But I'm going to x min at 0, x max at 2 over 19 pi. And I'm going to count my x scale. What am I counting by? Ooh, I don't know if that's easy to tell. Because these numbers are getting smaller, right? Wait a minute, let's think about this. 2 over 19 pi is teeny tiny. You follow? These numbers, so I'm actually going to go from 0 to 2 over pi. I don't know what I'm going to count by. I can't count by ones because I'm going to count by 0.1s just for fun. My y min and y max I'm going to make negative 2 to 2. Okay, is that fun? Not at all. So here's the first number I plugged in, 2 over pi was way out here. And then when I plugged 2 over 3 pi, we said I keep getting closer and closer to 0. So 2 over pi gave me 1. This must be 2 over 3 pi. This must be 2 over 5 pi. This is 2 over 7 pi. And I really, this is where it's an odd concept. There's an infinite number of oscillations between 2 over pi, which by the way is not even 1, right? And 0. Because I can keep getting infinitely close to 0, and every odd 2 over odd pi, even though that number can increase infinitely, that has me getting infinitely closer to 0. So here I'm going 0 to 2 over pi, and it kind of looks like I have, well, if we count this as a maximum, 1, 2, 3, 4, 5, 6. It's kind of hard to see. If I even shrink this up and I only look from 0 to 2 over 7 pi, and I really just like take a look in there, I could even zoom in to do that. If I want to zoom in on this part of the graph, you just see it go absolutely nuts in there because there's an infinite number of them, which is like a tough thing to wrap your head around. Anyway, we don't want to, that just looks like a barcode. Okay. So when this gets closer and closer to 0, it seems to oscillate back and forth, yes? It doesn't seem to, it's not like there's a hole at 0, right? It doesn't seem to hone in on a number. It just continuously will go back and forth. And for that reason, the limit does not exist, maybe? Right? We talked about oscillation in kind of the infinite direction. What do you observe as x approaches 0? The graph kind of goes nuts. There are, we'll say there are an infinite number of oscillations between -1 and 1 as we approach 0. Good? Okay, that's not the last we'll see of this graph, but just a weird concept to wrap your head around. Okay. Next one. A function we have, again, no idea how to manipulate this, right? This book doesn't really know that we understand the factoring, canceling, and manipulation process yet, but we know that we can't factor and cancel that. I also know that I'm not positive what this graph looks like. I know what a natural log graph looks like, but what happens when I divide it by x, not really sure. So least efficient method, but something we'll have to do, and for something like this we can use a calculator, is table of values. So if I plug in -0.1, and maybe I'll just do this with a table. Maybe I'll just graph it right out of the gate. So the natural log, rather than typing it in 1,000 times, the natural log of x plus 1, all divided by x. And if I graph this, I can do second trace value and just grab those all at the same time rather than plugging them in over and over again. So second trace, if I plug in a value of -0.1, I get 1.0536. If I do second trace value again and plug in -0.01, I'm going to get 1.005. And if I plug in -0.001, as I'm getting closer to 0 from the left, I get 1.0005. I probably should have gone out. Well, no, 1.005 and then 1.0005. So this shows me that my limit as I approach 0 from the left on this function, what's that getting closer and closer to? 1. Shrinking, shrinking, shrinking towards 1. On the positive side of things, if I do my second trace value for 0.1, I get 0.9531. If I then do 0.01, I get 0.995. And if I do 0.001, I get 0.9995. And so I would say my limit as I approach 0 coming from the right on this function is also 1. It's just it's increasing toward 1. And so therefore the overall limit as x approaches 0 on this function is 1. And I mean, here's the graph of it. You should see that it exists, right? But 0 itself doesn't exist. The function value doesn't exist because it would be the natural log of 1 over 0. What is the natural log of 1? E to what power gives you 1? 0. So that is 0. So if you directly evaluated, you would get 0 over 0, indeterminate. You try to manipulate, I have no idea how to manipulate that. You try to think of what the graph looks like, I have no idea what the graph looks like unless I type it into my calculator. So your only other option is to think about values. But of course we had a calculator for these values. But let's think about this. Let's think of this as two different graphs. On the natural log graph, which normally looks like this and crosses at 1, right? This particular graph got shifted 1 unit to the left. So there's your natural log of x plus 1. That one does have a limit as x approaches 0, right? That as x approaches 0, that's actually getting closer to, is it 0? Right? Natural log of x shifted 1 to the right. As x approaches 0, y approaches 0. And then for the denominator, the linear graph, which is just this, as x approaches 0, well, y is approaching 0 too, so that's giving us the indeterminate. This is getting infinitely small towards 0, if we like kind of look to the left and right, and this is getting infinitely small. So teeny tiny over teeny tiny doesn't really tell us much. Does that make sense? So our only option was to look at a table of values. Those are the tricky ones, and this may be something we never do without a calculator. Okay? We probably will never do without a calculator, because how would you ever know that that is 1? I'm going to double check with Mrs. Hill on that. Will we ever be able to do this without a calculator? But we use functions like this because they exist to kind of develop understanding of the overall concept. Okay, so your homework is page 72, 1 through 25 odds, and again, obviously that's out of your new textbook. And we have 5 minutes, so maybe I'll go ask her now. Nothing like a real-time answer.